This is a video covering the first kind of lesson having to do with gases and gas laws. So this is lesson 1, module 11. So gases, you should have already done the PHET, states of matter, and hopefully taken away that you can increase pressure on a gas by decreasing the volume or increasing the temperature or increasing the number of moles or particles. And we'll use the letter N for moles. The mass of the gas particles shouldn't have affected the gas pressure. In the assumptions for kinetic molecular theory, the mass and the volume of the particles are very small, that they're almost negligible. And lastly, the kinetic energy of the particles is the motion of them is directly proportional to the temperature in Kelvin. So if you increase the temperature, the kinetic energy of the particles will increase. So we'll start here. So kinetic molecular theory is it's a theory that we use to help explain behaviors of gases on all types of matter, but we're going to be focusing on gases. So the word kinetic means to move, and all particles, even in solids, are constantly moving. And we're going to talk about some of the assumptions. So these are assumptions for an ideal gas, and most gases do behave this way. Extreme temperature and pressures can make them not behave this way, but everything that we deal with will behave and follow these kind of assumptions. So the first one is particle size. Because the particles themselves are so small compared to the space between them, there's no real attractive or repulsive forces. Like gas particles don't really interact with one another. And sometimes we say that the volume of the particle is negligible because it's very small. Particle motion, just that the particles in gases and solids and liquids, constant random motion, random for the gases. So also when the particles collide, the collisions are elastic, which means when they hit each other, they don't lose any energy. Unlike like if a bowling ball hits another bowling ball, they're both going to bounce back with less energy than what they had started with, because some of the energy would be lost due to friction and heat where the balls hit each other. But for gas particles, this doesn't happen. There is no energy or heat loss. The elastic collision means that there's no energy loss. And this is true because if it were not true, every time the particles hit each other, they would lose a little bit of energy and eventually stop moving, which would be absolute zero, and that's not the case. Particle energy, so the temperature is a measure of the average kinetic energy. You can calculate. We won't, but the kinetic energy is equal to 1/2 mass times the velocity squared. So gases can be compressed in a closed container, and they can expand, and they will take up the whatever size container you give them. So pressure, we talk about pressure a lot, not so much, but pressure is part of our weather app usually, because when the pressure changes, it's usually when there's a different high pressure system coming in or a low pressure system coming in. So anyways, pressure is defined as force per unit area. And the reason we have pressure is because the gas particles are colliding with each other. And if they're in a container, they're also colliding with the sides of the container. So air pressure, there's not really a container in a way there is, because the gravity holds our atmosphere, close to the Earth. But the particles will, in the atmosphere, do collide with one another and create air pressure. And so when you get to a higher altitude, there's less particles because it's further from the center of the Earth, so the gravity is less. So there's less particles, so less collisions are going to happen. So the gas pressure goes down at high altitude. So we can measure pressure different ways. This is what we call a barometer. And you might have a barometer at home. We have one in school. It's not really an open dish of mercury like this, but this is still the concept of how it works. So in this diagram, it's the atmospheric pressure is pushing always on everything, not just down, but it is pushing on mercury, and that causes the mercury to go up the tube, and we can measure that height, and that corresponds to a pressure. So like I said, our devices now don't really just have mercury just sitting out, but it's still something sensitive in them that can feel that atmospheric pressure pushing, and then that translates to a value of pressure. A manometer is similar to the barometer in some ways, but also different. So the barometer is open, an open system, whereas this is a closed system or container. So now, you would have a certain gas that's creating a certain amount of pressure that would push on, again, something like mercury that's very sensitive to those changes, and that would cause it to rise or fall in the tube. The units of pressure, we use atmospheres. So normal pressure at sea level is 1 atm or atmosphere, which is equal to 760 millimeters of mercury, and that's also equal to 101.3 kilopascals. And then also 1 atm, a lot of our bikes and car tires are in PSI, which is pounds per square inch. So that one's not on your pink sheet, but if you ever need it, we would give it to you. You could add it right now, though, if you wanted. So on your pink sheet, there's a section about gases, and those pressure equalities are right here. So you don't have to memorize them. So let's look at this example. So we live, like I said, the air is always around us, pushing on us. If you notice in this picture, they call the air up on a mountain like Mount Everest thinner because there's less particles. You can this is just trying to show you that there's less particles higher up in the atmosphere, and then more when you get to lower or towards sea level. So in this example, we want to calculate the pressure on Mount Everest on just, one particular day. Let's say the pressure was 31 kilopascals. So we want to convert this into atmospheres. The height of the mountain is interesting, but not needed in the question. So 31 kilopascals, I know that there's 101.3 kilopascals for every 1 atm. So this is equal to each other. So I can make a conversion factor out of that. So I would put the 101.3 kilopascals here so that they cancel, and the 1 atm here. And then we would just crunch that on our calculators, and then also sig fig it. I'm going to say that those pressure, that 1 atm really has infinite sig figs. We'll say the 101.3 also does, although I think it is a rounded number, but still, those aren't measurements. So we're going to keep our 2 sig figs here. So when we get our final answer, it's 0.31 atm. So the pressure on Everest at that, this depends on weather too, but it's about a third of what it would be at sea level. So that's why people have to use oxygen tanks so that they can get more gas particles. Also, there's difficulties flying helicopters and things because there just isn't enough air around. Here is a question about the planet Venus. So the temperature of the surface is 872 Fahrenheit, and the pressure is about 1350 psi, so pounds per square inch, and that's about equal to the pressure if you were 3,000 feet under water on Earth. So it's a huge pressure. So anyways, So Venus has not got an atmosphere of oxygen and nitrogen like us, but an atmosphere with sulfuric acid gas. So that makes it hard for us to observe the surface. But anyways, what we're going to do is take that pressure on Venus and we're going to convert it to kilopascals. So if you remember, I'm gonna, if you want, you can actually add equals 14.7 psi. So all of those things are equal. So you can just choose the two that you're solving the problem for. So we know we're going to use the 14.7. And then what do they want? We wanted it in kilopascal, right? So then we'll use also the 101.3. So I'm going to put the 14.7 psi, pounds per square inch here, and the 101.3 kilopascals here. So then I'm going to keep the 3 sig figs that I'm starting with, and I should get, so I get unrounded, I get this number. So with 3 sig figs, I would want to write this in scientific notation as 9.30 times 10 to the third kilopascals. So a normal pressure at sea level for us is 101.3. So that is, very high pressure. Dalton's law of partial pressure is just stating that if you have a mixture of gases, whatever each of those gases' pressure is, the sum of those pressures is what the total pressure will be in the container. So the partial pressure of each of the gases depends on the number of moles, the container, the temperature, all of that. But it doesn't matter what type of gas it is. So that kind of goes back to that kinetic molecular theory that the mass and the volume of the particles is so small that we can kind of ignore them. So, really Dalton's law is just that if you have a container with a mixture, like let's say in this picture we have 2 different gases, the total pressure is going to equal the pressure of both of the gases, their individual pressures added together. So 1, 2, 3. They both have 8 particles. So maybe this has, 0.5 of an atmosphere. And this gas is also 0.5 atmosphere pressure. So then the total pressure would be 1.0 atmospheres when they're mixed together. So really simple questions, but we should do a couple. So here we have a mixture of oxygen and carbon dioxide and nitrogen. And we know that the total pressure is 0.97 atm. We're looking for the pressure of the oxygen. The partial pressure of the oxygen is our unknown. And the pressure of the carbon dioxide is given at 0.70. And the partial pressure of the nitrogen is 0.12 atm. So very simple. The total is going to equal the partial pressure of each of these gases added together. So we know, and these would all have to be in the same unit, and they are, but if not, you'd want to convert them so they're in the same unit. So I'm looking for pressure of O2, that's my X. The pressure of the CO2 and the pressure of the nitrogen. So pressure of the oxygen is really just going to be 0.97 minus 0.7 minus 0.12. So the partial pressure of the oxygen is 0.15 atmospheres. So you can always double check it. If you plug that in, you'll get 0.97. So that is all I have. I guess the only thing I would tell you is I think on the worksheet that you're going to practice, there's might be one where the pressures are not all in the same unit. So, if this had been given in like kilopascals, in order to add and subtract, they have to be in the same unit. So you would need to convert them before you do the simple math of adding or subtracting. And that is all I have. Let me know if you have any questions in class.